that we should continue. So I try to show you a few examples that how a non-equilibrium plasma can be used to enhance a combustion in scramjet engines, for example. So here is that a example that at Stanford University, Mark Capelli's group, they're using, this is that the scramjet cavity, they're using a cathode and an anode is a nanosecond pulse discharge, and to see that how that the nanosecond pulse discharge is going to enhance the combustion process. What they show that with that the nanosecond discharge, they can strongly enhance that the combustion process and produce more OH radicals and in a hydrogen scramjet. And this is another example about scramjet combustion done by Dr. Doe, and using arcjet. What it does is that using a arc, it's an equilibrium plasma, that they can heat that the reactant, and then here that is the cavity. So if this is the equivalence ratio. If you can look at the equivalence ratio, that when they increase the equivalence ratio, you start to see the flame that is stabilized in that the cavity. But when they go to fuel rich, that the fuel equivalence ratio and at 2.7 or 3.5, you can see that the flame and even move to the upstream. So this is a counterintuitive to many about the combustion people, because in combustion we say the flame speed is normally peak around equivalence ratio between 1 and 1.1. But between 1 and 1.1, you see that for example, the flame is around here, is 0.93, is 0.14. But if you increase that, they can propagate even upstream further, you can see. So this is clearly see that the combustion is not just enhanced by flame speed, and indeed, and it's enhanced by ignition very well, because at the fuel-rich conditions, ignition delay time is decreasing. So therefore, even though your flame speed is decreasing, but ignition delay time is decreasing further, that create a ignition-assisted flame stabilization in a scramjet engine. And other people, they try to choose using gliding arcs, because gliding arc is a combination that they have high electron number density and a higher electrical field and energy. So this is that done by, I think that in Notre Dame University, they're using this electrode, high voltage electrode and low voltage electrode. They generate this kind of gliding arc. This kind of gliding arc that flying around in the scramjet engine, and they can dramatically enhance that the flame stabilization in a scramjet. But the problem is that gliding arc requires a very high energy input. It is at probably several kilowatt or even more, and to enhance that but they can generate a very large volumetric discharge to enhance combustion. And recently, that this is the work probably done in China, and they're using this is at AC high voltage, and then this is that probably the wall is a cathode. They create this kind of a gliding arc, and along this wall, they can stabilize a combustion. So therefore, you can see both nanosecond discharge and also that the gliding arc are pursued, and in scramjet engine, try to enhance the ignition when the fly Mach number is lower. So another idea is that using microwave, and so this is an example done by which university? I think that is I don't remember which university anymore. But so this is basically using this microwave, and that they break down the critical discharge. So this is that the flow going a supersonic flow. They're using this microwave generator. This is antenna. They can create a strong electric field and break down discharge. They can stabilize the flow and in a high speed and 200 meters per second. I think that Van Ye and was the one conduct this job in Johns Hopkins University, and for a supersonic. So microwave can operate at a higher pressure and create a large volumetric breakdown. So many research show that a non-equilibrium plasma becomes very effective in enhanced flame stabilization and of high-speed combustion. So this is another work about that the plasma-assisted ignition or a detonation, a pulse detonation engine. And it's done at the Air Force Research Laboratory. So what they show that you have a pulse detonation engine is a detonation tube, and you need to enhance the ignition by a spark. So here is a comparison about a nanosecond discharge. You can see the nanosecond discharge can, at high frequency, they can create a fast ignition kernel and compare to a multi-spark. This is a multi-spark, and this is a nanosecond. So the reason, what is this? You have created one discharge, and that discharge created radicals. And then the next discharge is come in when the flow is moving, and so therefore that every discharge, they overlap each other. They continue to drive that the radicals to grow. That can enhance the ignition process in the plasma. So what it shows that the development time of flame and compared to that the energy input, you have more energy input in terms of nanosecond discharge compared to the spark discharge. That flame development time is getting shorter and reduced with that the energy increase because that you have less heat losses. So. And this is a typical example when you change that the frequency of that the nanosecond discharge is 2 kilohertz is 40. If you look at 2 kilohertz, you have one spark and another spark. The two sparks, they are not really connected to each other because the flow is so fast. So two isolated ignition corners. But if you have 40 kilohertz, that you have multiple discharge, they overlap, they create a big volume, and then eventually they can accelerate the ignition. And why that a big volume is important for ignition. And normally people think that ignition is just energy or temperature, but actually that's the ignition in a flow or ignition in an engine, volume becomes very important issue. We'll talk about that. So you can see this is the plasma discharge. You can one pulse, another pulse, another pulse. You can see that the radicals, this is that radical, more fractional radicals. They keep every pulses, the radical concentration keep the building up. So this is that they create a very important things that they try to overlap that the plasma discharge a volume that help them to connect into bigger volume to build the radicals, and is critical and to understand that the ignition process. So again, this is another example about rotational detonation engines. And the Pratt & Whitney, you can see that the rotational detonation happening. They have a lot of different kind of detonation cells and in the channel. Sometimes the detonation fails, and they form like a flame-like detonation. It's not detonation, it's like a flames. So in this case, that you don't have the coupling between shock wave with combustion, and detonation actually failed. So the question is that how do we accelerate the coupling between ignition and detonation so that they can increase the stability in a rotational detonation engines. So this is an experiment around probably a few years ago, around 2020, that we try to say that in order to understand how much that plasma can enhance detonation. So in order to do this, this is that the acetylene oxygen mixtures, if we put 1% of ozone into that mixture, and this is at a channel about a millimeter width with a probably less than 1 meter long. So you can see by adding just 1% of ozone created from plasma, you can see that this is without ozone, this is with ozone. You can see detonation transition is dramatically accelerated and intense. So with 1%, but then DDT speed is the same because the heat release rate overall does not change. So this is another example to showing that how using plasma to create ozone to change that the chemistry can modify DDT process. I think this is probably the first experiment demonstrate that. So later that my student at Madeline and right now is Andy is doing this plasma discharge and in a channel to in situ with a plasma DBD plasma discharge and to see how that plasma can affect the detonate DDT process. You can see this is the time after ignition. You can see that there's some low temperature ignition and the DDT process. And with plasma, you can see that the DDT process is dramatically accelerated. With a lot of plasma, DDT can be decelerated. So if you plot that the velocity as a function of time, you can see the green one that is without any kind of plasma discharge. And then the red one is with plasma discharge. You can immediately say that the flame accelerate and become a overdriven detonation and it become detonation process. And with a lot of plasma discharge and you become delayed. So the reason is very clear. It is because that with a few pulses of plasma discharge, you generate a lot of radicals and enhance low temperature combustion so that accelerate the ignition process, then you accelerate detonation. With a lot of plasma discharge, you consume the fuel and in the mixture. So even detonation happens, they try to happen, but they don't have enough energy to generate coupling between combustion wave and shock wave. They can see that the combustion happening very earlier, but they don't have enough energy to couple them, and they take a very long time and for detonation transition. So what does the experiment show you? Show you that using plasma, you can either activate it or you can delay it, provide a tool to control and the detonation process. So this is that the new experiment, probably more likely that it will be presented in a symposium by Andy. You can see that when you have a flame, you generate a precursor shock wave, and with a ozone and accelerated combustion, you generate a ignition front. That ignition coupling with a shock wave, that you can accelerate detonation. And another research in France was doing compare that the plasma without plasma, and they can see that the plasma can dramatically change that the cell size about detonation. Again, the size of cell size is is dictated that your shock collisions, which is ignition time. So both from the dynamics of DDT transition and from the cell size, and the experiment basically show that non-equilibrium plasma can accelerate ignition, and the chemistry can change the detonation process. So then this is about the high-speed propulsion. And internal combustion engine, a few years ago, Air Force, they want to look at that UAVs with the internal combustion engine. This UAV is very small. They only probably have 35 milliliters engine size. So they are so small. They can only operate at fuel rich conditions because that at the nearly stoichiometric or fuel lean conditions, and the engines start to, very rough or either start to fail. So the question that how can we enhance that the ignition process and make that the engine can operate at fuel lean conditions. So in that one, we work with imaging engineering by introducing a microwave into the system and see how that stabilize the ignition process. So in combustion process, which I presented before, and advanced diesel engine today probably is about below 50% of efficiency. And then you have the energy losses to exhaust 26%, and to the cooling, the 29%. And if you're looking at the temperature about a diesel engine or gasoline engine, the temperature actually is 2,500 or even higher, the peak temperature. So if you calculate the Carnot efficiency or auto efficiency, the Carnot efficiency is close to 90%, and auto efficiency is above 70%. But yet, your engine efficiency is only 40-some%. So most of the reason is because of the cooling. So the question is that how can you reduce the cooling? Without reducing cooling, you really cannot improve the efficiency much. It is that try to enabling that the lean burn or enabling that low temperature combustion process. So that is trigger a lot of research in Japan through this kind of science innovation program. You try to enabling that this combustion control and lean burn process, and also that the low temperature combustion to reduce the flame temperature. So they can, within a few, 5 years, they increase efficiency from 39% all the way to 55%. So combustion, understanding that the combustion process and establish lean burn and low temperature combustion through this technology innovation. So here they have using this kind of a gliding arc, that because spark cannot ignite that in the lean mixture, they want to using gliding arc so that they can ignite that the mixture at the linear condition, improve the efficiency. So and the corona discharge has also been studied because the corona is the metal rod, and you can fire that the plasma, let's say in 50 nanoseconds, you can see a volumetric discharge. They can enhance that reduce ignition delay time. For example, spark ignition, this is that the corona ignition. They can, at least by factor of 2, to reduce that the ignition time in engines. So so people want to say, okay, corona they can use in microwave. So what they do that they're using a nanosecond pulses that create breakdown, they generate a lot of electrons, and then they fire a microwave to gain that the energy of electrons, and then making that the combustion stronger. So particularly for small-scale engines, the heat losses between the electrodes is so large, so that this kind of microwave-assisted combustion can enhance that increase the combustion volume and increase the ignition probability. So this is what we did with imaging engineering using a microwave. Here is that the electrode, and it's a nanosecond discharge on here, and then there will be a microwave propagated through this antenna into this process. So a spark in combination with a microwave, and also some of the gliding arc. So you can see that this is the engine. With say spark only, that you can see a very small ignition happening. With spark with a microwave at 6.25 milliseconds, you can see a large volumetric ignition happening. If you look at that, the OH radicals, you can see clearly that the spark plus microwave give you a huge OH production, and then the pressure build up is also accelerated, and then flame area is increased. So all this kind of thing is a phenomenological research in the early days. They're all pointing to one conclusion. Plasma can do the magic work. They can enhance the flame stability. They can accelerate detonation. They can do X, Y, Z, a lot of things. So again, for this kind of small engines, and the four-stroke and small engine, you can see this is that the air-fuel ratio. This is a near stoichiometric, and you can see the original engine that only operate at near stoichiometric conditions. Is that but with a microwave and enhancement, they can extend it probably by 30% about that operation, and make that the small engine operating at the fuel lean conditions. So this is again to see when ignition become a problem, and the plasma has a great opportunity and to help. But there are some other contradictory experiments. This is done by in Berkeley by Dibble, Professor Bob Dibble. And he did this microwave and spark ignition and in a CEFRC chamber. What he sees that the flame development time with a spark and a microwave is similar to what I did. That indeed it was reduced, which is a good thing. But when he plot this second thing that called flame development time, after that the 10% of the flame kernel size is increased, they found that with a microwave has no impact in flame time acceleration. So this creates a big argument. Why do we see an enhancement of plasma-assisted combustion, but on the other hand, there's not much plasma enhanced at the flame speed? So what is that the ignition is governed in terms of enhancement, but without any increase of flame speed? So this is that the big thing. They see the similar things. They can burn fueling, they can extend the flammability limit, but the flame speed never changed. And even though they can do it. Why that the flame speed, without flame speed change, and then the lean burn limit is extended, and then that the flame develop time is enhanced. So that's what's a fundamental question to ask. Again, what we try to summarize that a plasma can enhance engines, but that the flame speed cannot be enhanced. And what is the reason? To answer that, and there was a paper, and my student and Chen published a theoretical analysis about how an ignition kernel become a flame. So imagine this is the flame speed, normalized by adiabatic flame speed. This is the radius of flame kernel. So if you have a small plasma energy, and the flame kernel will be ignited, but as the flame expand, the flame speed drop and quickly die. Remind you that this is that the Lewis number is larger than 1.2. You probably took that the Paul Clavine's class. You know how Lewis number is going to affect the flame. The larger the Lewis number, that means the flame is stretched. That means the flame is weaker with the stretch. But if you increase that the energy of ignition, you can see the flame speed is decreasing as it is going down, and they reach to a minimum speed. But after that, the flame speed pick up by itself and reach to 1, that is adiabatic flame speed. This is why that Bob Dibble and in Berkeley, they see that with plasma, there's no change of flame speed. Yes, there's no change of flame speed if the flame propagates outside. But if the flame kernel is very small, you see a big change with the plasma. But if the energy is higher, then you can see the flame decrease and dramatically smoothly transfer to adiabatic flame speed. So what does it say in this figure? This is the theory. It says one thing, that even in flammable mixture, does not mean that you can ignite it unless you can drive that the initial ignition kernel past this critical ignition radius. This matters. This is why. Because even though the mixture is flammable, if you cannot drive the initial ignition kernel bigger than this critical radius, you cannot ignite it. This gives a very clear guidance to design a future igniter using plasma that is to using a plasma to drive a spark or drive a discharge. It's bigger than RC, and then you can always successfully ignite it. So these are, to do that, and then for example, a Stavrik Kaya at France, and she wanted using this kind of surface gliding discharge. You can see that when you have high electrode here, and you have dielectrical materials, and then when you fire that is the high voltage, you generate all these kind of streamers. This streamer is gliding along the surface, and that create a large ignition volume. So this is what she shows here. It says that, okay, so this is the pressure, and this is the temperature, and with different mixtures. So at the gliding, with the surface gliding arc, they can accelerate the combustion process extremely well. For example, you can see from here with no discharge, with discharge, and no discharge, with discharge. And they can make the combustion accelerate with a discharge. So ignition energy matters, but most importantly is that ignition volume matters. So that is the first principle about the ignition enhancement. Again, so they tried this surface discharge at a high pressure and using hydrogen and oxygen mixtures, and they took this high-speed image to see how the discharge is happening and how the ignition process is doing. So surface discharge and provide open a new direction that they can operate at higher pressure, and also that open near the wall. So if somebody wanted to do catalysis research, so therefore this surface discharge maybe become very important that create the reactivity and as surface, and also can operate at higher pressure. Laser ignition has been pursued a long time, but I don't think that there's a lot of development today, and Toyota was one of the drivers to using a laser ignition to create this ignition. The idea, again, is the same, that they try to create a multiple ignition kernel, so that create a bigger ignition size to accelerate ignition. This is very effective if you can do it, because you can generate a large ignition volume. But that the optics and all this kind of stability at the high temperature, it becomes questionable for application of this laser ignition. And at Princeton, that Rich Myers, and they using this kind of femtosecond laser. So femtosecond laser is very strong electric field. They can pre-ionize the air and to a certain extent. So once you pre-ionize the air, you generate electrons and generate ionization. Then you fire a high voltage between the two electrodes, and this, the streamers will form from here and catch this pre-ionized region, and you can control the ignition at the location you want. But using femtosecond laser and is very expensive to do an ignition job. But the principle is very clear. The pre-ionization that can guiding the plasma channel can lead to plasma discharge at the location you want. I think this is the major conclusion we have. Other examples like the flame stabilization, a lot of work done by a group of Chris Laux in France and Lacoste, the group. They do a lot of flame stabilization. The idea that they want to have a nozzle, and they put the electrode and form a plasma nanosecond or radio frequency, and it become a flame stabilizer, and so that the plasma can continuously supply radicals and heat, so that flame will not be blow off. So what they show that the extinction limit was reduced by 10% with the plasma power with 75 watt. It's very moderate. So they also did this kind of two-stage swirling combustors with a plasma discharge, and they found that the limb burning limit again is reduced with plasma power of 300 watt. So you can see a lot of paper published by this group. They basically show that with a nanosecond plasma discharge, and you can stabilize at the limb burn limit, and with a moderate or small plasma energy compared to the combustion energy, which is true. So plasma is indeed important. I think today probably for UAVs, many of the UAVs, they have to fly at a different altitude, and different altitude will require a different ignition volume. So how to make the UAVs efficient, and say right now there's a lot of interest in that area to design a plasma to help that flame stabilization in UAVs. And so this is another experiment is in kerosene oil and using a nanosecond discharge. They also said that, okay, the limb burn limit is reduced by half. This is significant. Normally for methane, for propane, for jet fuel, the limb limit is almost 0.45 or something. If you can reduce it by half, that is a significant extension about the limb burn limit in terms of plasma. So, and they studied that the nanosecond discharge on fueling combustion. So this is at the electrode, and this is another electrode, and they generate a plasma here, and they flow this air propane mixture, and they measure the flow velocity. They found that the 3 different regimes, stabilized flames, and this kind of lifted flames, they come with very short flames. And what they show that the equivalence ratio, and with a plasma, and they can reduce that the flame stabilization equivalence ratio with a plasma discharge. You can see here, particularly at the nearly fueling conditions. So, and all these kind of things that has been demonstrated in 10 years ago, or to show the effectiveness. And in the last few years, really, that for me, that if I say for high temperature combustion, it's easy to understand that if you have a plasma, create radicals, they can create heat, you can stabilize combustion. For me, my focus is that, is low temperature combustion, it can be established by plasma. Can we see a cool flame stabilized in plasma? I think that a cool flame had been observed a long time ago, but no one really can see a cool flame just in the lab stabilized. So I understand the plasma can do it, but I want to see a plasma can stabilize the cool flame in the laboratory. If you're looking at that, the low temperature ignition timing in the engine conditions is less than 1 millisecond. If you look at that, the gas turbine and also the gasoline engines, their timescales are, you look for the, from spark to combustion is about a few milliseconds as well. So turbines combustion has a lot of timescales. So therefore, this kind of low temperature combustion is relevant to all these engine conditions to control. So this is the picture by skiing, and they showing endodecane spray into the high temperature air environment. They start to see this cool flame, this formaldehyde formation. A large amount of formaldehyde formation is always indicating that you have a low temperature combustion is happening. So therefore, what it sees that if you have a jet fuel or is a diesel fuel into the high temperature, the low temperature starts first. And that they create radicals affecting what is happening afterwards. So therefore, it's not low temperature chemistry not important. Rather, it's very important, but normally you don't see it because it's so fast. So here that computation, I like this by Damps. He computed this in countable flame. It looked at the time scales about the equivalence ratio. And what happened that in the beginning in this process is that you have a ignition. This ignition they call cool flame ignition. It's happening at fueling conditions. Why is the fueling conditions? Because they need high air temperature to make ignition happen. So once the low temperature ignition happening, that the cool flames start to propagate to fuel rich conditions. You look at the equivalence ratio, and because the rich condition doesn't need much temperature, and at this fuel rich conditions, that generate a lot of radicals, and OH radicals start to build up, and heat release start to build up. Once the heat release and radical build up, that trigger high temperature ignition. The high temperature ignition drive that flame back to stabilize nearly stoichiometric. So this diagram clearly shows what happening in an ignition process. Low temperature ignition start at the high temperature fueling conditions, that the ignition kernel will flash back to the rich conditions is everything by ignition. And then the ignition build radicals, create heat release, the hot ignition happening. Once the hot ignition happening, they become a flame stabilized there. So therefore, the whole combustion process is a low temperature ignition, high temperature ignition to flame transition. So the question to me was that, can I control this low temperature combustion by plasma part? So that is a very interesting thing. So always I show this a good picture that the God brought the fire into earth, and this artist plot this figure in flames that have different colors, red and yellow, orange and white, and I didn't understand why. And today that we have become very clear that the cool flames that was first discovered by Davy 200 years ago. At that time, they put a very rich, for example, dimethyl ether mixtures. They put a metal into that very rich mixture. They start to see a bluish flame and fluctuating in front of the metal. So, and that was the first discovery about the cool flames. After that, NASA they fly a microwave gravity experiment, and they see that the very rich butane and propane mixtures, they can autoignite a cool flame from the center and propagate to the wall. But no one really can see stabilize the cool flames in the laboratory with a few link conditions. This is what happened with the plasma support. And my group, and a few years ago, we can see the cool flame stabilized by ozone or by plasma. We can start to see a hot flame. We can start to see a double flame. That means that the hot flame follow a cool flame. And that really dramatically advanced the understanding about that the flame regimes of low temperature. And so we can experimentally, we can see this flame temperature as a strain rate in a counter for flame. And we can see that at high temperature, you got a very sooty high temperature flame. At the low temperature, you got very cool flames. And in the middle, there's a warm flame. You can see there's a double flame structures. That is the first one is that the cool flame front. The second one is HO2 chemistry, the governing a warm flame structures. This is that the RO2 chemistry. This is the HO2 chemistry. This is H plus O2 chemistry. So now that why you understand that the artists plot the three flames, because they have God created three different flames in nature, right? That was so fascinating when I understand this and can be able to see in the lab. And also plasma, ammonia right now become a very hot potato. And a lot of people try to do ammonia combustion. But ammonia is dictated by a lot of NOx emissions. So recently, that the people in Montaigne and at Georgia Tech, they studied that how with plasma, without plasma, certainly with plasma, you can stabilize the flame, and very well in ammonia combustion. Particularly, flame speed is very low. But most importantly, what they say that the NOx emission this is with plasma. You can see that with plasma, no plasma is here. With plasma is there. And this is voltage. You can see that with plasma, the NOx is reduced. That is unbelievable, but most people in hydrogen combustion, if you put a plasma there, suddenly your NOx is formed. But ammonia is very different. Ammonia, you can see that this is that the reduction. If we have plasma, can create more N in the ammonia combustion, the N reacts with NO, then can reduce into nitrogen. They call reburning process. If you can break down ammonia into NH2, for example, the NH2 will react with NO and reduce that the NOx becomes to nitrogen and water. So that reaction probably is that the plasma can break down the fuel into NH and NH2. This NH and NH2 react with NO. They form a reduced to nitrogen. That becomes one of the interesting. And I think this the conclusion is quite clear with laser diagnostics. But I think that we need to understand quantitatively how fast this reaction can be in comparison to plasma process. So what I try to see that by using plasma, some magic can happen, and you can do something. And typically combustion cannot do in terms of reactions. Another example about the ozone reaction, and how the plasma can generate ozone with ethylene. And what he showed that this is that the ozone addition. So in here, that when you see if you increase the ozone, the flame sitting back to the burner. Here, that when you increase the ozone, the flame lift off from the burner. And it was understanding why that at different flow conditions, at high speed, they lift off, and then the lower speed, they flash back. So that is because that is the ozone reaction with ethylene to create a low temperature chemistry that accelerate the oxidation and makes the flame propagate. But if the flame speed is high, the flame is lifted, the low temperature chemistry created that the fuel quickly mixed with the environment and make the flame very lean, so that the flame doesn't have the strength to flash back. Instead, it will be blow off, that lift. So again, what I try to see that this is happen at room temperature. So the plasma process and they create a interesting chemistry. They typically may not easily to occur in a combustion environment. They can change the flame stabilization and change the emissions of a combustion process. So this ozone lysis reaction, they can be very clear. They made a formaldehyde PLIF. They can see that this with a different ozone level, the flame propagated back to the burner, and you can form a lot of formaldehyde, is indicating a low temperature oxidation process of ethylene assisted by ozone. And also that when you have different conditions, you can also see a formaldehyde formed, and when the flame is lifted off. But in this case, it is formed a lot of formaldehyde, which is good, but you have a lot of diffusion, and the formaldehyde will diffuse to the surrounding, making that the flame heat release is weaker, so that flame will be lifted off. So this is why that happens at a different flow velocity. You can see some magic is happening. And also that people did this kind of a soot emission using a plasma discharge for diffusion flame. They can using a plasma increase the voltage. You can see that the soot is dramatically reduced. And here that is mostly is because of the ionic wind. When you have a plasma and you create this oxygen ions or you have water ions, that ions move, that they create ionic wind. The ionic wind will pre-mix some of the fuel with the air. You can, by pre-mixing the reactant, and you are going to reduce the soot emission. So a lot of people in the plasma do using electrical field instead of discharge to control the ionic wind for mixing. But this kind of research, I think that is very difficult to be applied to real combustion systems, because ionic wind highly depend on the scales of your burners, and then the flow rate, and the combustion mixtures. So that's very hard to be really applied. But it's very interesting to study the mechanism about this. So really that is what we showed you a lot of magics, and in combustion, something can do, and they can pretty much do everything. And the question is really that what is the dust plasma is really just play a thermal effect, or the plasma really have some chemistry effect that can enhance the reaction pathway or create a new reaction pathway. And that if yes, how does the plasma kinetically enhance ignition and flame speed and the minimum ignition energy, which are very important for combustion? What are the reaction pathways of plasma-assisted combustion? So these are the things that lead to fundamental research, because all what I show in previous 30 to 40 minutes are the impact. When you're writing a proposal to a program manager, you have to show the impact first. And then you tell them what is the mechanism you want to understand. So that is something we want to talk, and 15 minutes. Let me see whether we can talk a little bit about the mechanism about plasma-assisted combustion process. If we cannot finish it, we can continue. I think that many of you took that probably Professor Paul Clavine's talk, and you understand what is the ignition, what is the flame speed, and but I want to give you a quick review that you take one step back and what really plasma can do and cannot do. So we want to talk about the plasma effect on ignition limit. We talk about the plasma effect and on flame propagation, extinction, flammability limit, and the cool flames, and then critical radius. So everybody knows that in flames, that flame is governed by exothermic, self-accelerating chain branching process that make flame can propagate. And you can have a premix flames like this, that flame propagation speed and fuel and oxide heat release, adiabatic flame temperature. You can have a diffusion flame like a candle flame. And at high temperature, everything is governed by this reaction and chain branching reactions. So therefore, that the Dancourt number is defined by that the time scales of transport, flow, or diffusion, and normalized by reaction time scales. You want a flame to be alive, that you have a flame Dancourt number equal to 1. But typically in combustion process, people assume that the ignition Dancourt number is almost 0. It means upstream that the fuel and oxygen mixture, the ignition Dancourt number is almost 0. It's called chemically frozen. That is the assumption. But if you have plasma in upstream, this assumption does not apply because you have reactivity in the unburned mixture. So therefore, that if you have a premix flame and you are bounded by these two limits, they call lean burn limit, rich burn limit. The flame can only stabilize in between. So all the plasma people want to do, they want to extend this lean limit to here, the rich limit is there, so that they can control the combustion in a more efficient way. And in a diffusion flames, and you are different. If you have ignition, flow resistance time is a temperature. So when you increase that flow resistance time, ignition will happen, the form of flame. And when you reduce the time, that they don't have time to react, and then they die. This is called ignition, flame, extinction. It's very typical. But on the other hand, if we continue to increase the diffusion time, and then the flame volume becomes very big in a diffusion flame, and then you create a lot of thermal radiation from the flame, and eventually the flame will die. And this is called, by radiation extinction limit, this is called straight extinction limit. So this premix flame, both of them, they're governed by radiation. But premix flame, you don't need diffusion. I mean, anyway, you just, the radiation kill you. The radiation heat loss makes this chain branching will not occur. But for diffusion flame, there are two things, stretch, and then you have radiation extinction. And so understand that is very important. So if you're looking at ignition time, you have governing equations, and then you integrate these equations, you can find what is ignition. I don't have time to follow, but I try to give you a result. That in the end, you can derive a ignition time is a function about that the beta is the activation energy, reaction coefficient, this is the activation energy here, and temperature. When you look at this equation, you can see how plasma can enhance ignition. The plasma can reduce activation energy by creating new reaction pathways, by raising the temperature, that you can accelerate a Newton's law, and also that by changing the reaction rate about the B. So these are the potentially from ignition, the plasma can enhance the process. So you can also what if plasma, you have heat losses? Well, if you have heat losses, that the ignition will be, ignition time will increase. But with the plasma, that you have heat gain. So this process become a heat gain. So therefore, your ignition will be a decrease due to that the exothermicity of plasma. So you can simply derive a equation about heat, how that the heat generation by plasma can affect this. But if you're looking at, zoom into it, if you're looking at the plasma chemistry for radical production. So in air, that one of the most important reactions is this. Electron impact with oxygen form, oh, this, you're missing an electron here. There should be an electron here. You generated one atomic oxygen, one singular delta. This singular delta is very reactive. They can, one collision, they can grab an H from that the fuel, or they can insert into the CH bond to form a OH functional group of the fuel. So also at the electron impact with oxygen, they form this oxygen, singular oxygen molecules, and with a very low temperature. And this singular oxygen molecules, they can react with few radicals. They can accelerate combustion as well. And you have a electron-ion recombination process. This gives you heat, fast heating, charge transfer. And you have this kind of, in the air, you generate dissociation reactions through excited molecules. For example, electron collide with nitrogen, create this electronically excited nitrogen. And these electronically excited nitrogen can react with oxygen to form two O atoms. These two O atoms, just like this, they can well accelerate the combustion process. If you have O singular D radicals reaction with fuel, or O2 molecular singlet reaction with a radical, both of these reaction channels are 3, B and C. They are much faster than the ground state. So in other words, radical production in the process, electronic state, excited molecule production, and in the plasma, they are going to change your reaction rate or change your reaction pathways. And for example, this vibrational state and also give you interesting, for example, methyl reacts with HO2. These are the key reactions in methane oxidation. Methyl plus HO2, the form formaldehyde plus OH. But this reaction typically is very slow. That's why ignition of methane is very slow. But if we can vibrationally excited to create this HO2 vibration, you can accelerate this reaction. So what I'm trying to say is that in the plasma process, you have fast heating and slow heating, but also you create this kind of electronically and vibrationally and the radicals that can manipulate the reaction process for ignition and the combustion process. So for example, if you have a hydrogen, if you're adding a H atom, an OH atom, and O atoms, you can see that by adding O atoms, the ignition delay time is much shorter by adding H and OH. This is very clear because this reaction and this reaction is very fast. By adding an O atom here, this reaction is fast, they create the OH and H. And this reaction is even faster, they create a H again. So adding O means you're adding 2 H atoms. If you're just adding H, then that's it. If you're adding a OH, if you're adding OH because this one is very fast, you give you H. Adding OH and H is the same thing. But in adding O, you can create 2 OHs that make that the reaction is faster. So therefore, understanding that the chemical kinetics, which one is rate limiting, is very important process in terms of plasma cystic combustion and the kinetics. And this is the experiment we done and at Princeton, and a long time ago when I became an assistant professor, we tried using gliding arc to gliding around and in the air, try to create that, see whether the flame speed, flame stabilization can be enhanced by plasma chemistry, or ignition chemistry can be enhanced. So this was funded by Air Force to understand what is the mechanism, with earlier studies in the United States about how plasma affects the combustion process. So here is at the ignition temperature. You can see that without no plasma is here, and with plasma, you can see that by using a gliding arc, the plasma ignition, the ignition temperature can be dropped by about 100 degrees. So all of this reason is because that HO2 formation that can form a plasma form a NOx. The NOx reaction with HO2, they form these OH radicals. So therefore, it's not much about atomic oxygen generation. is more about this NOx coupling with HO2 at the low temperature. They give you OH radicals, enhance the combustion. So therefore, plasma can create this kind of atomic oxygen, but also create the NO2 that is coupling with a low temperature combustion process. And so this is that the flammable ability limit diagram, that ignition limit. So this is that the first limit, is the second limit, is the third limit. They are governing by different reactions. The first limit is typically by H plus O2 reaction, termination reaction. This is by the second is the competition between branching and termination, and third is HO2 chemistry. And if you use in plasma, you can see that you can break down this kind of ignition limit. And there's no ignition limit in terms of plasma. So that you can see that the plasma process. So if you really do a simple analysis about kinetics, you add in this reaction into that is a hydrogen combustion mechanism. You do a simple quasi-steady-state analysis, you can see that the H radical production now is a function not only governed by the competition between branching and termination, but also by this plasma reaction rate. This new terms due to this oxygen production reactions will break that the ignition limit diagram to a different stage. So what about the methane? For methane, everybody knows that the methane reaction is very slow. The slow is that the methane, this methane reaction is dictated by this methyl plus oxygen to form methoxy. This methyl reaction with HO2 reaction is extremely slow. And so therefore, that if you can use in plasma, that can create a lot of HO2 at a low temperature, because HO2 is formed at a low temperature and in this way, so that you can enhance the low temperature oxidation of methane. So this is what the simulation kinetics of methane oxygen. You can see this is that the auto ignition. You can see that the ignition delay time very long. And here, this is plasma. You can plasma create a lot of species, and before that ignition happening. So this radical species then help that the ignition to occur much faster. So the shaft tube experiment by Andrei Sarkovsky here, yeah. So they try to see that how ignition delay time is changed as a function of temperature. This is the methane and auto ignition. This is the plasma-assisted ignition. You can see the ignition delay time measured in the shock tube is reduced by 2 orders of magnitude. So these are the experimental data, and they're showing you how plasma created fast radical generation in plasma can accelerate ignition process. Okay, probably I'll talk next tomorrow. So we try to say that radical production by plasma that can accelerate that the combustion chemistry or ignition chemistry can break that the limit of ignition. And so in next class tomorrow, we'll try to talk about how that the radical production that particularly in plasma, they can change low temperature combustion and then detonation process. All right, well, thank you for any questions so far?